This section we're going to be going over indefinite integrals and the net change theorem. So this is kind of merging with the previous section that we have done. We're going to be going over the notation for antiderivatives, and hopefully remember the formulas for finding antiderivatives and use them to evaluate indefinite integrals, as well as definite integrals. So something that I think I mentioned sort of accidentally in the previous section, the term definite integral. I think I just said it in passing in the previous section. Definite integral has bounds or limits of integration, and an indefinite integral has no bounds. Okay, so an indefinite integral, as we're going to see, is going to have a plus c, and a definite integral will not have a plus c. So that means a definite integral will give us a number answer, and an indefinite integral will give us a function answer with a plus c. Okay, so we're going to go over both of these, starting with indefinite integrals. So the notation, which we have seen already, right? We've seen this notation in the previous section, is going to be read as the integral of f of x dx, and it's used for finding the antiderivative of f of x. And this is going to be an indefinite integral because there's no limits of integration, or there's no bounds. So if we take the integral of f of x dx, it's going to equal capital F of x, where capital F of x is the antiderivative. Okay, so we've kind of already have seen this. So let's go ahead and check out this example. So we can rewrite the integral of x squared dx as x cubed over 3 plus c, because if we take the derivative of this, it equals x squared. So just remember that antiderivatives and derivatives are opposites. And we can always check our answer here for indefinite integrals by taking the derivative of the answer and making sure we end up with what we started with. And just like I mentioned, what's written down here, indefinite integral is going to be a family of functions, called a family of functions because the constant plus c can be anything, and the definite integral will give us a number. So here are the table of indefinite integrals that you're going to need to remember. And we should actually already know them because they are just the antiderivatives. So taking the integral of something is finding the antiderivative. So let's go through these quickly. If you're taking the integral of a constant times a function, you can bring the constant out front and then rewrite it like this. If you're doing the integral of multiple functions being added, you can do the integrals of them separately and then add the result. And that's same thing with subtraction, obviously. If you're doing the integral of a constant, all you have to do is multiply the variable onto that constant. And then notice all of these have a plus c at the end. If you're doing the integral of a power function, x to some number, then you add 1 to the exponent and divide by that new exponent. However, n cannot be -1. If n is -1, that would result in this right here, the integral of 1 over x, which we know is the ln of x plus c. We know that the integral of e to the x is just e to the x. The one that's a little bit tricky that we don't really see as often is the integral of b to the x, where b is a number. A positive number not equal to 1 is going to be b to the x divided by ln of b. So it's actually the more general version of e to the x, because if we were doing the integral of e to the x using this formula right here, that would be e to the x over the ln of e. The ln of e is equal to 1, so it's just equal to e to the x. Okay, and then moving down into the trig functions here, the integral of sine of x is negative cosine of x. So you have to be careful because the derivative of cosine is negative sine. So it would have to be taking the derivative of negative cosine would give us negative sine, which would be positive sine. Okay, and then the integral of cosine is sine. The integral of secant squared is tangent because the derivative of tangent is secant squared. And the integral of cosecant squared is negative cotangent. And that's because the derivative of positive cotangent is negative cosecant squared. The integral of secant x times tangent x is secant x. Integral of cosecant x times cotangent x is negative cosecant x. And then the last one gets a little bit tricky. The integral of 1 over x squared plus 1 is actually tangent inverse of x. And the integral of 1 over the square root of 1 minus x squared is sine inverse of x. I don't know if I just misspoke on this one. I don't know if I said tangent or sine by mistake, but that one is tan inverse. Okay, so make sure that you just have all of these memorized and you know how to use them. And when we are doing this or doing these integrals, we have to know that it's only valid on a certain interval. So for example, if we're doing, let's say we're doing the integral of 1 over x squared. So doing the integral of 1 over x squared, we could rewrite that as x to the negative 2, add 1 to the exponent, divide by that exponent. We would end up getting x to the negative 1. Negative x to the negative 1, or 1 over x. And since it's an indefinite integral, we always have that plus c. And we have to know that this is only valid when x does not equal 0, because x cannot equal 0 for 1 over x squared. So it's only valid on the intervals negative infinity to 0 and 0 to infinity, not including 0. Okay, so let's do a couple examples here. So we want to find the general antiderivative. So that means we're doing, when you see the word general antiderivative or general indefinite integral, that means we're going to have a plus c at the end. Okay, so we're going to find the integral of 10x to the 4th minus 2 secant squared of x dx. And all we have to do here is find the antiderivative of each one of these separately. So the antiderivative of 10x to the 4th, we're going to add 1 to the exponent and then divide by that new exponent minus 2 times secant squared. The antiderivative of secant squared is tangent. Right, so the derivative of tangent secant squared, and hopefully you just have that memorized based on the previous page. And since negative 2 is a constant, it just comes along for the ride. So once we have those two done, all we have to do is add in a plus c at the end, plus any constant. And then we have to simplify. So simplifying 10 divided by 5, we get 2x to the 5th minus 2 tangent x plus c. So the indefinite integral here gives us a function as our answer. And something that you can always do is you can check the answer by taking the derivative, making sure you end up with what you started with. Okay, and then just obviously remember that differentiating plus c, differentiating a constant is 0. Okay, next example. Once again, this is an indefinite integral because we don't have limits of integration. We don't have any bounds on the integral sign. We want the integral of cosine theta over sine squared theta d theta. So trig ones can get a little bit tricky because we might have to use some sort of trig identities. And the reason why we have to use trig identities is because cosine theta over sine squared theta does not have a nice antiderivative for us. You'll see that it does, but we need to rewrite it first to be able to identify it. Something that we cannot do is we cannot say that this is equal to the integral of cosine divided by the integral of sine squared. That is not true, so make sure you are not doing that with the integral symbol. Same thing for the same reasons why we couldn't do that when we were differentiating. So what we're going to do is we're going to actually rewrite this as cosine theta over sine theta times 1 over sine theta d theta. So notice all we did here was chop up the denominator. Instead of sine squared, we wrote it as sine times sine. And the reason for this is because now we can rewrite cosine over sine. This is the same as cotangent. Right? Cosine over sine is cotangent. That's a quotient identity, just like tangent is sine over cosine. And then we can also rewrite 1 over sine as cosecant. That's a reciprocal identity. Cosecant theta is equal to 1 over sine theta. Okay, so now we're doing the integral of cotangent theta times cosecant theta. This is actually one of the things that we should have memorized if we go back to our table. That's this right here. The order doesn't matter, right? Cosecant, cotangent, doesn't matter which one comes first because we're multiplying. The answer here is going to be negative cosecant x plus c. So this integral is negative cosecant, in this case theta, plus a constant. Okay, and then once again, we can go ahead if we wanted to, and maybe let's actually do it for this one. Let's differentiate. I'll put check. The derivative of, well, let me do d theta, I guess. d theta of negative cosecant theta plus c. The derivative of negative cosecant theta is going to be negative, and then the derivative of cosecant is negative cosecant theta times cotangent theta. And the derivative of the constant is 0. So the negatives cancel off. We get cosecant theta times cotangent theta. So we check, is this what we started with? And it's right there, so yes. Okay, so those were indefinite integrals. Now we're jumping back to definite integrals, and we should remember how to do this. We have to use the fundamental theorem of calculus 2 and antiderivatives. So we're going to find the antiderivative and then do upper bound minus lower bound. Okay, so finding the antiderivative here of x cubed, add 1 to the exponent, divide by that exponent, minus 6x. So we add 1 to the exponent, divide by the exponent, and that's it. We don't need a plus c because it's a definite integral. Now we plug in the bounds. So evaluated from x equals 0 to x equals 3. And we do upper bound first. It's going to be 3 to the 4th over 4 minus, well, actually, let's just simplify this real quick. I'm going to write this as 1/4 x to the 4th minus 3x squared. Just clean it up just a little bit, and now let's go ahead and plug in the upper bound first. So we get 1/4 times 3 to the 4th minus 3 times 3 squared minus, so notice here that when we plug in 0, it's actually going to cancel both of these terms. So I'm going to do a little bit of foresight and say that that's just going to be 0. Remember, that will not always happen, so just verify before you actually plug in that 0. So 3 to the 4th is 81. 81 over 4 minus 3 times 9, so 27. And we could get common denominators. I'm just going to write this one as a decimal. We get negative 6.75. So that would give us the net area under the curve from 0 to 3. And we can see that the area is going to be more negative. There's going to be more area below the curve than, more area below the x-axis than above the x-axis because we got a negative answer. Next one, determine the following and interpret the results. We want the integral from 0 to 2. So once again, we have a definite integral because we have these limits of integration of 2x cubed minus 6x plus 3 over x squared plus 1 dx. Okay, so we need to do the antiderivative of these three terms separately. So let's take a look at the first one, 2x cubed. So this is going to be add 1 to the exponent and divide by that new exponent. Next one, 6x, add 1 to the exponent, divide by that new exponent, so 6x squared over 2. Next one is a little tricky. We know that we could rewrite this as 3 times 1 over x squared plus 1. The 3 is a constant that's coming along for the ride. And then the antiderivative of 1 over x squared plus 1, this one is tangent inverse of x. So don't make the mistake of just trying to add 1 to the exponent and dividing by an exponent. You can only do that when it's just one term, x, raised up to an exponent. So a little bit tricky for that one. And now we're going to evaluate this whole thing from 0 to 2. I'm going to clean this up a little bit first. The first term is 1/2 x to the 4th. Second term is 3x squared. Last term stays the same. Now let's go ahead and evaluate by plugging in upper bound minus lower bound. Okay, so plugging in the upper bound, that's 1/2 2 to the 4th minus 3 2 times 2 squared plus 3 times tan inverse of 2 minus, let's go ahead and actually plug in the 0 here, just so we know that we can't always skip that step when it's a 0. So we plug in a 0 for the lower bound, and we get this whole thing. So what actually ends up happening is that this whole thing does equal 0, so we could actually just cancel this whole thing out, this whole entire right side. But I just wanted to make sure that we know that that doesn't always happen. So we go ahead and evaluate this. We would get 8 minus 12, so negative 4, plus 3 times tan inverse of 2. So this is the exact answer right here. If you wanted a decimal answer, you can just plug it into the calculator, because tan inverse of 2 is obviously not going to give us a nice answer. So I'll say that that is approximately negative 0.67855, once again depending on if it wanted a decimal answer or the exact answer. Okay, so moving on to the next one. We want to evaluate the integral from 1 to 9 of 2t squared plus t squared radical t minus 1 all over t squared dt. So before we do anything for this one, we should rewrite this. So we can rewrite this by splitting up the fraction. We can give everything in the numerator its own denominator. So that would be 2t squared over t squared plus t squared radical t over t squared minus 1 over t squared. Put that whole thing in parentheses, dt. Now let's see if we can even simplify further. That's the whole reason for doing this. And we can. Notice that the t squareds cancel in the first one. T squared divided by t squared equals 1. So we're left with 2 plus. Also notice that the t squareds cancel in the next one. We could have tried to combine t squared times radical t, but then we would have had to simplify with the denominator anyway. So just notice that these cancel right away. So we're left with radical t. Instead of writing radical t, write t to the 1/2. Right, because we're going to need to rewrite it like that to apply our little formula to it. And then for the next one, 1 over t squared. Anytime you have 1 over a variable to an exponent, put it in the numerator and make the exponent negative in this case. If there were a constant other than 1 up here, it would just come along for the ride. Okay, so now we can just go ahead and apply the rules to each one of these terms. So the integral of 2, that's a constant, so we have 2t, plus the integral of t to the 1/2, add 1 to the exponent, divide by that new exponent, 1/2 plus 1 is 3/2. Last one, add 1 to the exponent, and divide by that new exponent. So just be careful when they're negative exponents and you're adding. And we're evaluating this from 1 to 9. So before we evaluate this, let's go ahead, simplify one more time. Instead of dividing by 3/2, you can multiply by 2/3. Right? Dividing by something and multiplying by the reciprocal are the same thing. And dividing by a negative, or subtracting and then dividing by a negative, will cancel to a positive. And t to the -1 we can rewrite as 1 over t. Okay, let's go ahead and plug in now upper bound minus lower bound. So we plug in a 9. So 2 times 9 plus 2/3 times 9 to the 3/2 plus 1 over 9. Minus, now we plug in the 1. So that's going to be 2 times 1 plus 2/3 times 1 to the 3/2 plus 1 over 1. And let's go ahead and simplify each one of these. This is going to be 18 plus 9 to the 3/2. What you could do is the square root of 9 is 3. And then 3 cubed is 27. 27 divided by 3 is 9. 9 times 2 is 18. So we should be able to do that one in our head. It's just doing one little step at a time. And then plus 1/9 minus 2 plus 2/3 plus 1. And we'd have to get common denominators if we wanted a fraction. We would get 292 divided by 9. So that's one version of our answer. And we could also get a decimal if we want. The decimal ends up being 32.4 repeating. I'm just going to leave it as a fraction. Okay, so that is it for this one. Something I just forgot too from the previous one. The example said to interpret the results in terms of areas. Sorry to jump back. So interpreting this result in terms of areas. And as we know, that number represents the net area under the curve of that function from x equals 0 to x equals 2, which were the limits of integration. Okay, so sorry, just forgot to write that down. Okay, so that brings us to the last thing here for this section is the net change theorem. So this is going to be using the fundamental theorem of calculus 2. If we take the integral of a rate of change, So the integral of the rate of change is the integral of a derivative. The integral of a derivative is something called the net change. So this is the fundamental theorem of calculus 2. We find the antiderivative, plug in upper bound minus lower bound. So this is useful because there's so many applications. And we're just going to mention a bunch of applications and then do one of them. So one application is if we have V of t, and that's the volume of water in a reservoir at time t, then its derivative, V prime of t, is going to be the rate at which water flows into the reservoir at time t. So that means this integral from t1 to t2 of V prime of t dt is going to be the change in the amount of water in the reservoir between t1 and t2. Okay, so that's one example here. Next one would be an example for the concentration of the product of a chemical reaction, which I won't really go over, but it's the same exact idea. Next one is the mass of a rod measured from the left endpoint to some point x, and from there we can find the linear density. And from there, we can actually find the mass of a segment of a rod. Okay, so I won't really get too much into that. Next important one is the rate of growth of a population. So population growth. And then the last one, which is what we're going to do an example of, is if we have an object that moves along a straight line with a position function s of t, then the velocity is the derivative of position. So I think we've worked with this before. We have a position function, which we denote s of t. We have a velocity function, which we can find by taking the derivative of the position function. And if we really want to, we can find the acceleration function by taking the derivative of velocity. Okay, so from that, we get this setup right here using the fundamental theorem of calculus 2. We have the integral from t1 to t2 of v of t dt. That's going to represent the difference in position or displacement. So taking the integral of velocity over some time frame gives us the change in position, the net change in position, which is called displacement from t1 to t2. So before we do an example, let's talk about the differences in displacement and distance. We just said that displacement is going to be the net change in position. What that means is it's the distance from where the object started to where the object finished. Okay, so how does that change from total distance traveled? Distance traveled is just the total distance that the object traveled over that time period. So let's think about, before we look at this graph, let's think about an example. Let's say that you are walking in a straight line and you are starting just at like an origin. If you take five steps forward and then 5 steps backwards and then 5 more steps forwards, let's think about the difference in displacement and distance traveled. So the displacement is going to be how far are you from where you began. Well, if you take 5 steps forward and then 5 steps backwards, you're right back where you began. But then if you take 5 more steps forwards, your displacement is 5 steps, right? 5 forward, 5 backwards cancel out. 5 more forwards equals 5 steps for displacement. Total distance traveled here is going to be 15 steps. So 15 steps, you think about all of these as being positive. You take 5 steps, you take 5 more, you take 5 more, that's 15 total. Okay, so that's the difference between displacement and distance traveled. Let's take a look now and do this with integration. Say we have this curve and the area here is positive, area here is negative, area here is positive. If we just took the integral of this function from t1 to t2, that will give us displacement. So just taking the integral will give us displacement. Notice how it's going to be, first one's positive, then negative, then positive. So displacement is just taking the integral. If we want the total distance traveled, or the total distance traveled for this, we would want to add up a1 plus a2 plus a3. We would have to think about all of these as positive values. So the total distance is going to be doing the absolute value of the function and then taking the integral of that. That will give us all positive areas. Okay, so make sure you know the difference here between displacement and total distance traveled. And let's do an example here of actually integrating. Okay, last example here. A particle moves along a line so that its velocity at time t is v of t equals t squared minus t minus 6, and this is measured in feet per second. We're going to find the displacement from 1 to 4 and also the distance traveled. So it is important that we're moving in a straight line, or else we would have to do a little bit other stuff involved. So everything we do is going to be in a straight line. Okay, so from what we just learned, displacement is going to be the net change in position, and all we have to do to that is take the integral of the function from t equals 1 to t equals 4, and our function is, we're doing that with v of t. We said that that's going to be equal to, well, let me just go ahead and write this on the side real quick. The integral t1 to t2 of v of t dt is going to equal s of t2 minus s of t1. That gives us the displacement. So we go ahead, plugged in our lower bound of 1, upper bound of 4. Our velocity equation is t squared minus t minus 6 dt. And then all we have to do is just evaluate this definite integral. So we're going to find the antiderivative of each term, add 1 to the exponent, divide by that exponent, add 1, divide by 1, and then the antiderivative of 6 is 6t. Plug in our bounds, 1 to 4. And I trust that we can evaluate these now. If we do that, we would get negative 9 over 2. So let's think about what this means. Well, displacement being negative means it moved in the negative direction, and we're going to take the left to be the negative direction. That means the particle would move 4.5 meters, because position is in meters, if velocity is in meters per second. It moved 4.5 meters to the left. 9 over 2 is 4.5. Since it's negative, to the left. Okay, so it ended up being 4.5 meters to the left of where it started. Next, let's go ahead and find the distance traveled. And the distance traveled is going to be a little bit harder. So our goal here is to find the integral from t1 to t2 of the absolute value of our function v of t. So what we need to do first is find where v of t is negative, and then we're going to make that answer, we're going to integrate it and then make that answer positive. So v of t is t squared minus t minus 6. T squared minus t minus 6. Let's go ahead and see when this equals to 0. We can factor this as t minus 3 times t plus 2. We get t equals negative 2 and t equals 3. So if we went ahead and graphed this parabola, right, this is a parabola, t squared minus t minus 6. We have negative 2, positive 3. We know it's crossing through here and here, and we actually know that it has to look like this because it has to open upwards because the t squared is positive. So now we can see exactly where the function's positive and negative. We are only interested in the interval from 1 to 4 though, right? We're only interested in this portion right here from t equals 1 to t equals 4 because that's our interval for this question. So I'm just going to put some little vertical lines, t equals 1 to t equals 4. So we can see that the function is negative from 1 to 3 and positive from 3 to 4. And I'll say less than or equal to 0 just so I can include the endpoints. And then it's positive greater than or equal to 0 on the interval 3 to 4. So the whole point of this was to find where it's negative. We just found that it's negative on the interval 1 to 3. That means when we're integrating, we actually have to integrate negative v of t over this interval. We're just going to make that answer negative, essentially. Right? Because if we already know it's negative, so to make it positive, negate a negative, it becomes positive. So the distance traveled is going to be the integral from 1 to 4 of the absolute value of v of t dt, which is going to become, now we chop up our interval 1 to 3 and then 3 to 4. So it's going to become the interval from 1 to 3, where we said we have to do negative v of t plus the integral from 3 to 4. Since it was positive here, we just do the positive version of v of t. Okay, so let's go ahead and do this. So negative v of t integral from 1 to 3. I'm just going to go ahead and, so here is v of t. I'm just going to negate that every term. That's negative t squared plus t plus 6. If you wanted to, you could bring the negative out front. It doesn't matter how you do it. You'll get the same answer. And then for the next one, we have plus the integral 3 to 4 of the original v of t. And now we have to do both of these integrals separately. So I'm going to go through and do it kind of quickly. The first integral becomes negative t cubed over 3 plus t squared over 2 plus 6t evaluated from 1 to 3. And then the next one becomes the same thing, but every term is just the negated of what we just did. T cubed over 3 minus t squared over 2 minus 6t evaluated from 3 to 4. So if we went ahead and we actually calculated that out, which I recommend you doing to make sure that you can, we would get 61 over 6, which is going to be about 10.17 meters. Okay, you can see how distance traveled is a little trickier. You have to find when the function's negative and then chop up the integral and then negate the negative portion to make it positive and then integrate separately. So the total distance traveled was 10.17 and the displacement was 4.5 meters. Okay, so that is it for this section.